Hello grade 9s, this is Mr. Miller and welcome to lesson 6.1 on representing patterns. So in part 1 here, we want to draw the next two figures in this series. Let's have a close look at that. So figure number 1 has these 3 squares, figure number 2 has 5, and figure number 3 should have 1, 2, 3, 4, 5, 6, and 7. So let's label this as figure number 3. Next, we're going to do another figure. And this time it's going to have 9. So here's 2, 3, 4, 5, 6, 7, 8, and 9. So again, this is figure 4. Next, we would like to create a table of values comparing the number of squares and the figure number. So, how about if we refer to the figure number as n, and we'll refer to the number of squares as s. And now we'll just take a look at setting up a t-table. Alright, so starting at figure number 1, notice that there were 3 squares. With figure number 2, we counted that there were 5 squares. So we continued that pattern on. With figure number 3, there were 7 squares. And with figure number 4, we ended up with 9 squares. So in order to go on to part C, where it says to describe the pattern in words, it's useful to examine exactly how changes are occurring in both in the figure number and in the number of squares. So let's do that. So first of all, you'll notice that the number of squares is always increasing by 2. Whereas the figure number is always increasing by 1. Also of particular importance to us later is going to be the value of the number of squares when the figure number is 0. And although we don't have a figure number 0, let's just say hypothetically, what if? So that's working backwards a step, and working backwards a step in the number of squares would subtract 2. So as a result, when our figure number is hypothetically 0, we would hypothetically again have the number of squares being at 1. So those are going to be some key things that we're going to use in coming up with an equation. And in fact, my preference is actually to come up with the equation first that represents this pattern, and then to talk about this pattern in words. So with all of the relationships that we're going to be looking at in Math 9, they are going to be linear relationships. And we know that it's a linear relationship because there's a constant ratio between the change in the number of squares and the change in the figure number. It's always 2 over 1. So now we can indicate that the number of squares s is equal to a certain number times the figure number and plus or minus a little bit of something else. So I'm going to give you a surefire way of coming up with all these things. So first of all, let's come up with the coefficient of n. And we can do that by looking at the change in s over the change in n. And as you can see here, the change in s over the change in n is equal to positive 2. So I'm going to use that as the coefficient of n. My plus something else is the s value when n is equal to 0, which turns out to be 1. Once I have this equation, it's often easier to come up with, to me anyways, the pattern in words. So what I can write here is the number of squares is 1 more than twice the figure number. So now again, I just want to highlight exactly how we came up with this equation. So recognizing that it's a linear pattern, a linear relationship, because there is a constant ratio between the change in the number of squares and the change in the figure number. That's a 2/1 ratio each time. Because of that, I can write it as s equal to something times n plus or minus something else. To get the coefficient of n, we take the change in the number of squares over the change in the figure number. That's how we got 2 as our coefficient here. And the plus something else is the s value when n is equal to 0. Now just to prove that this works in each case for the values that we have in our table here, let's use s equals 2n plus 1 to check that we get the correct s value for each n value. So if n equals 1, s is equal to 2 times 1 plus 1. That would be 3. So that works. What about if n is equal to 2? We'd have 2 times 2 plus 1. Well, that's 5. So it's still working. With n equals 3, 2 times 3 plus 1, that gives us 7. 2 times 4 plus 1 gives us 9. So you can see that for each of these n values, we get the correct s value using this equation. So now that we know we have the right equation, it's really handy because we can figure out how many squares are in figure number 15 without having to go through all of the other values in this chart. So we can calculate the number of squares in figure number 15 just by plugging 15 in for n. So 2 times 15 is 30, and adding 1 to that, we get 31. The other thing that we can do is we can figure out if we have a figure with 69 squares for s, then what should the figure number be? So 69 is what you get when you do 2 times n plus 1. So you can probably figure out that 2n, therefore, would be 1 less than that, at 68. And so that means that you'd have n is half of that, which is 34. So now moving on to page 2, it says here that a number pattern starts at 1.5 and increases by 4 for each number that follows. First off, we want to make a table of values for the first 5 terms. So let's take a look at x and y values. So the first number is 1.5. The second number is 4 more than that, which is 5.5. The third number is 4 more than that, so it's 9.5. The fourth number is 4 more than that, so it's 13.5. The fifth number is 4 more than that, so it's 17.5. And so on. So now we want to come up with an equation that can be used to determine the value of each term. So notice that I've left some empty space here. And that's because, just as we did before, we want to be able to work through this, figure out working backwards to the 0th term, if you like. What would that be, hypothetically speaking? So do we have a linear relationship here? I don't know. Let's take a look at the change in x and the change in y. So the change in y is going up by 4 each time. And the change in x is going up by 1. So now if we work backwards to, hypothetically speaking, what if we were at the term number 0? Then what? So working backwards, we would have to subtract 4 from 1.5, which would take us to negative 2.5. And so in developing an equation that can be used to determine the value of each term, first of all, we look at the fact that the change in y over the change in x is always a constant. It's 4 over 1. So doing 4 divided by 1 gives us 4 for the coefficient that we should use in front of x. So each y value can be calculated by doing 4 times x and adding on the y value when x is 0. So now we can find the value of the 95th term very easily from this formula. We can simply do 4 times 95, and then we can add negative 2.5. And when we do that, 4 times 95 is 380, and adding negative 2.5 is like subtracting 2.5 from that. So this would give you 377.5. We could also answer questions such as this: which term has a value of 237.5? So this time it's the y value that's given to us, which is 237.5, and we need to figure out what is the x that works in this case. So first of all, if we've added negative 2.5 already and we end up with 237.5, you can understand that the 4x therefore should be 240. And now taking a quarter of that, you get x is equal to 60. So this refers to the fact this is the 60th term. In number 3, it says, on top of the $45 monthly fee, Sam's cell phone plan charges 15 cents for every text message that he sends or receives. Develop an equation to calculate his monthly bill. So first of all, if we let capital C be equal to the cost and T be equal to the number of text messages sent in a month. So I guess we should indicate the cost for a month. So then the equation would be C equals 45 plus 0.15 T. And that's because of the fact that there is a constant cost of $45 per month plus a variable cost which depends on the number of text messages sent. It's 15 cents per text message. You have to multiply by the number of text messages that are sent. So now let's complete a table of values comparing the number of text messages and the monthly cost. So we're going to start off with the number of text messages being 0, and what would be the cost of that, and that would be just $45. Now if you send one text message, there's an additional 15 cents, so it would be 45.15. 2 text messages sent, it would be 45.30, and so on. 3 text messages sent would be 45.45. Now, I don't think this is a particularly realistic example, but it gives you an idea of how you can use linear equations to understand something like this. So hypothetically speaking, what would Sam's bill be if there were 20 text messages sent in a month? So if we know that it's a $45 cost automatically, and then it's 15 cents per text message times the number of text messages, which is 20, we can calculate it like this. So it's $45 plus it's going to be an extra $3 for those text messages for a total of $48. Now it says if Sam budgets $80 a month for his cell phone, how many text messages can he send or receive each month? So if $80 is the cost we're looking at, maximum, and that's $45 plus 15 cents per text message times the number of text messages. This is the cost with the basic monthly fee. Take a look at just what is the cost of those text messages. The 0.15 times T would be 80 minus $45, which is just $35. And now if we want to know how many text messages can be sent, we do 35 divided by 0.15, and when you do that you would get on a calculator 233.333 and so on. He should stay within 233 text messages so that his bill is less than $80. With 233 and a third, of course you can't send a third of a text message, that would give you a cost of exactly $80. As soon as you go to 234 text messages, it would go above $80. So that's the end of the lesson. Thanks for watching and have a great day.